let's begin with a review of lecture 14. And today, I hope to be continuing on data structures and to complete the section on data structures. And then from next time, we should be able to go on to the next topics. So we will next look at the linked lists and their applications. So far, we've looked at linked lists in a fair amount of detail, but we're going to take a closer look at linked list applications today. And we'll also see how you can perhaps create linked lists using Python. And there's something called Python dictionaries, which we'll look at. And then we look at other applications of linked lists, including how to manage memory for processes. And then we look at something called binary trees and something called a binary search tree. And time permitting, we'll also look at some other issues. So review of the last lecture, we looked at the issues of arrays sorted and unsorted, and we looked at how the complexity compares in terms of memory utilization and doing various operations on arrays. And we saw that, well, there was a trade-off between a sorted array and an unsorted array, right? So in other words, the unsorted array was very slow in terms of search, but it was fast in terms of insertion and deletion, whereas a sorted array was much faster in terms of search, but it was slow in terms of insertion and deletion. In terms of memory utilization, they were both the same. And then we looked at a linked list, and we said that if you want to search through a linked list, it's still taking an order of n time. We then looked at only deletion after assuming that you have already found the specific node, and that was taking constant amount of time. And then we looked at the insertion time, and this included the search time, and so this was taking order of n. So essentially, the summary was that if we looked at the unsorted, sorted arrays, and then compared it to linked list, there was a trade-off. So the major advantage of using a linked list was that it was much more memory efficient. However, it wasn't very good in terms of searching. For example, the sorted array was actually better. Insertion, the unsorted array was actually better, and deletion was about the same. Well, deletion, it was reasonably good as compared to an unsorted array. And so the question was, can we do better? And clearly, we're not really satisfied with the performance of the linked list as it exists, simply because the search is taking order of n time, and also insertion is taking an order of n time. Okay, simply because the search is taking order of n time. And although it's very efficient in terms of memory utilization, however, this basic issue is something that we need to address. And so last time we sort of stopped at looking at different operations of linked list. We saw how you can append, and you can make it a little faster, the search, by adding a tail pointer. And then we said that if you want to make it properly operate, the tail pointer to properly operate, you actually also need a reverse pointer, okay? And that was somewhat helping. So even after doing a doubly linked list, we were still at the same point that the search wasn't much better than order of n. So now we, hopefully by the end of this lecture, we will try to see if we can find a better algorithm, perhaps using a linked list, which can essentially address this basic flaw, okay? And before we get to that, what we'll try to do is introduce some of the complexities in linked lists and try to get a better handle of linked lists so that we can understand the solution once we see it. So let's take a look at the different applications of linked lists. And we'll start off by simply looking at what we've seen before as well, a single list in which you have different data types, okay? A list with different data types, as you know that Python allows that. So here you have an integer, here you have a string, a real number, and a Boolean. And the question is, how would you convert this, or how would you store it as a linked list? Okay. So I would like people to suggest solutions for that. Can you think of a linked list architecture, a structure, whereby you could actually save this list as a linked list with different data types? Okay, so this shouldn't be too different from what we've already discussed in the past, but I would like people to give suggestions. So I've already got a pointer, L1 in memory, 500. And we're starting off with a node over here, and we're saying we could have multiple nodes, but what is the contents of the nodes and what are the pointers and so on. So please give some suggestions. Any suggestions? '15th lecture. All right. Is the course becoming too complex for people? I hope people are still going to contribute in terms of giving suggestions. So let me try to elaborate further. So the question is, what should be the content of this linked list? Clearly, you need to have different data types in it. Okay. If you remember, we've talked about this earlier as well, that you could have different data types, but somehow we've got to be able to manage an integer and a string, a Boolean, a real number, and Booleans all in the same linked list. So how would you do that? Okay, so the first node would clearly have the number 10 in it, the integer 10. The second node would have the string high in it, all right, and so on. So where would we put the integer, and how would we make sure that the system can actually recognize the integer and not get confused as to whether it's an integer or it's a string? Okay, suggestions. Put on your thinking caps, and I'm sure that some of you can give some good ideas. Not are people.
Can you repeat the question?
So the question is, what would be the structure of the linked list? Okay, so I'm creating a linked list. So in the past, we've already seen linked list. So here is a linked list, which is a double linked list. Okay, this was a single linked list, which was simply the numbers, the numbers 600, 700, and so on. Sorry, this was a linked list with the numbers 1, 2, and 15 kept in it. But now what we're doing is we're not just putting in integers in this linked list. What we're trying to do is we're trying to create a linked list with different data types. Okay, so for example, if it was just a bunch of integers, you could have the number, let's say if it was the number 1 and this was the number 5 over here, you could simply have the number 1 over here, number 5 over here, and we could have a pointer over here. Okay, and then if let's say the next number is 15, we could have this linked list, right? And at the end, we would have something like a null pointer to the next pointer. But now the numbers are not just integers. These could be integers, or they could be strings, or they could be Boolean. So how do we create this structure?
So we can direct a pointer to virtual memory to select the string.
Okay, very good. So if you're saying that if it's a string, we can have a pointer to another portion of the memory. Okay, and that's a very good suggestion, because what that would allow us to do is have a variable size string. Okay, so for example, if it's high, at the end we'd have a null over here. That could be accommodated because it's a pointer to another portion in memory. But if it's a much longer string, such as hello, then this pointer would be able to accommodate a larger string as well. Excellent suggestion. So that takes care of the string. And so you're saying that there should be a pointer. If this is a string, then the next thing should be a pointer. Okay. But what if it's simply an integer? So let's say you're trying to store 10. Then how would you organize this node, this data structure? Would you need a pointer in that case? Let's say we're storing the number 10 over here. Would you still need to have a pointer to somewhere in memory where you're storing the number 10? Would you need that? Or could you store it
So
direct?
Heather again.
Heather.
Heather again. I think no, you can just keep it like that.
Okay.
You don't need.
So the reason why the number 10 can be just kept over there is because it's not fluctuating in size. It'll, let's say if it's a 4-byte integer, then it will always take 4 bytes. So there's not a problem in terms of variation in the size of this data type. Okay, very good. Now, how do you determine whether the content 10 is actually is an integer, or in this case, it's a string? So let's say if I kept the pointer over here, the first thing is a pointer, then how does it know that this is actually a pointer and not the actual integer itself? How does it know how to interpret the first byte or the first bytes in that node? So what do we need to have initially?
So we can have like leading figures or leading numbers that could like specify like 00 could specify it's a pointer, 01 could
Very
specify
good.
it.
Okay,
Heather.
so you've got it right. Basically, what you're saying is that initially, that first byte should be able to specify, just like we discussed earlier, that first byte should be able to specify whether you're putting in an integer or a string or a real number or a Boolean and so on. Okay, so we could have the first, let's say, byte as the type, and the next information that comes in that node would would be determined by this type over here. So for example, if let's say we have an integer over here, then we could store the number 10 over here. And if we have a string over here, then we could store the string. So I've shown this over here. So basically what we're doing is we're creating a bunch of nodes which are linked together in a linked list. The first portion, the first initial portion specifies the type. So here we have this is an integer. So this is specified as an integer, and we have the integer because then the system knows that the next the next bytes after the type is going to be of a certain number of bytes of integer. Okay, and if it's a string, then it should know that the following bytes will actually specify a string. Okay, and if it's a float, then it will have a floating number. And if it's a Boolean, then there should be some maybe 1 byte which will have a true or false. And after that, there should be a pointer. Okay, and the pointer will point to the next memory. So do I have a mistake somewhere in here?
Sir, Shahan here.
Jishan.
Sir, there's no reverse pointer like the reverse pointer that we discussed in last class.
Okay, so one of the things is that we don't have a reverse pointer, and that could be useful if you're trying to go in the reverse direction. Okay, that's good. But just the structure over here, is there a problem over here?
Yeah, hi is oh sorry, Ryan.
Yeah.
Hi is not like string is not stored like that.
Yeah.
It's just version.
So ideally, this should be a pointer. Okay, I'm making some mistakes, perhaps deliberately, to make sure that people are awake. So it will actually, this should actually be a pointer. Okay, so this will specify that the next thing that's coming in is a string, and whenever you have a string, it will actually be a pointer to another place in memory, and the actual content should be over here. Okay, but the others, because they're fixed size, can be in the actual node itself, and this node will actually be a complicated node.
Sir, Muslim, I have a question.
Give me some.
Would we say this is contiguous or non-contiguous?
You tell me. Can somebody answer that question? Is all of this contiguous or non-contiguous?
Not contiguous, sir.
Yeah, this is non-contiguous. That's the basic difference between, remember between arrays and linked lists. And the reason why this is wasteful is because it's storing it in contiguous memory, and so you need to pre-allocate a lot of memory. And this is efficient in the larger view of this problem because it's using non-contiguous memory, and it's only allocating memory as and when needed. Okay, so it doesn't have to beforehand allocate a whole large chunk of memory. So this is all non-contiguous. So far we've understood how a linked list would actually store a list of different data types. Now let's make this a little bit more interesting. This is a mistake, so this should actually be a pointer. Okay. So now the question is, some of you might have tried this out, but in Python, what you can do is you can type this, L1 is equal to this. L1 is a list itself, and L2 can be a list which has another list embedded inside it. Okay. In other words, this is a hierarchical list. And if you print this out, if you print L2, it will print 20, okay? And then it will print L1, the entire list L1, and that is from here till here, okay? And then it will print the third element of that list, which is by. So what you're seeing over here is what can be referred to as a nested list. And you can imagine that you could have another L3, which includes L2 and L1 as well. So you could have a whole hierarchy of lists embedded in other lists. Now, this is very interesting, and Python allows that. And this shows you the flexibility that some of these languages allow. Now, can somebody tell me how would you actually create L2? Right, so we saw how L1 could be done. And L1 itself was slightly hierarchical because, as you saw over here, this was itself a pointer to another node, a smaller node, which was basically a string. But this was basically the high-level nodes, which had a certain structure, which had the type, and then followed by the actual content, except in the case of a string where it had a pointer. Okay. Now, how would you create L2, which is now a hierarchy of strings? Any thoughts on that?
Sir Musab.
Sir.
Ji, Musab. Yeah, I think
Sir, we would create,
Ji.
yes, we create the list L2, and
Yeah.
after 20, we'd have a pointer that points towards the start of L1.
Okay.
And at the end of L1, we'll have a pointer that goes towards Y.
Perfect. Super. So you create L2, and you would say that this is an integer, right? And it has the number 20 in it, and then it points to the next node. I think this is what you're saying. And the next node is actually now a list. Okay. So now what we're going to do is create another type. Earlier, we only had integer, string, float, and boolean. Now what we'll do is introduce a new type, and we'll just call it list. And the list should have as its next element what? I think you said that it should have a pointer. So this would be a pointer to what? To the L1 itself. So L1 can retain its location in memory, and L2 will simply have a pointer to L1. Okay, and then it will have the next pointer to the third element, which is by over here. Okay, and that will be another, it will be a string. So this will be a pointer to a string, and that will have BYE and maybe a null at the end. And then this will be a null as well, which will look something like this. Okay. So does everybody follow this? And let me just show this to you over here. Okay, so this is L2. It's this is the new node that we've got. It's list of type list, and it has a type pointer as its element. Just like as in string, this element was supposed to be a pointer, and in the list itself is also a pointer, but in this case, it's going to point to another list. Okay, so this was the original list. So this is getting a little complex, I can understand that, but I hope people are following this. You can see the power now of using linked lists. You can have a very complex, arbitrarily complex structure, and linked list can do all of that while maintaining its efficiency. All right. So let's say if you did print L2, how would that actually do the printing? It would come over here to the first location, and assuming that there is no, it doesn't really need at present backward pointer. It's simply going to go through this. It will print the number 20, go to the next item, then it'll see that it's a list, so it'll go to the beginning of this list, It'll print the integer, it'll go here, it'll print the actual string over here, come back here, go to the pointer, to the float, print this, and then it will end up over here, it'll come back over here, go to this next element, and then print the string. And then it'll end the entire list too. So I hope this is clear as to how we've got a list embedded in another list. Okay. So if this is clear, we'll continue. If there's any question, please let me know now. All right. So now let's try to understand how Python actually deals with linked lists and so on. So as I said earlier, sometimes Python is not the best language to demonstrate these things. And I don't want to switch to another language to demonstrate linked lists, simply because that would be very confusing. So I'll demonstrate, try to demonstrate it in Python, but I'll just like to tell you that this is not exactly how Python data structures will work. Okay, but this will give you an idea as to how linked lists can be created in Python. To truly understand that, you would have to understand object-oriented programming, which won't be covered until the next semester. Okay, and it involves classes and so on. But I'll show you a simplistic version of how Python can create data structures. So we'll use something called dictionaries. Okay, now if you think about what a dictionary is, can somebody tell me what is the basic data structure of a dictionary? How would you describe that?
Sir, this is Mohammed Amar.
Yamar.
Sir, it basically stores values and keys and values.
Okay, excellent. So it stores keys and values. Okay, so what does that mean? It implies that basically you can think of, let's say here's a data structure called a person. Okay, now for example, the person has a certain name. He has a date of birth. He has gender, and he has a certain height. Okay, he or she. So what we're going to do is the dictionary data structure, basically, as Mars just pointed out, has pairs. Okay, and these pairs basically comprise of a key and a value. Okay, so this is the first pair. The key here is name, and the value is the name Ahmed in this case. The next key is date of birth, and the keys are always in inverted commas. The value may or may not be a string. So for example, the date of birth is just a year, so it could be stored as an integer. So right away, you can see that this dictionary consists of data types of different types. Okay, so here this is a string, this is an integer. For example, here you're storing whether the person is male or not. So if the person is male, you say true, otherwise you say false. And for the height, for example, you may store a floating number. Okay, so when you print this out, it will print it. When you print person1 out, it will show you as pairs. So this is the first pair, name is Ahmed. This is the second pair, date of birth is 1990. Third pair is that he's male. And the fourth pair is that his height is 5 feet 5 inches or 5.5 feet. Okay. Now, the unique thing about Python dictionary data structures is that the key has to be unique. In other words, you can't have two date of births, right? You can't have two heights, you can't have two names, and so on. If you want to have two names, for example, first and last name, then you would have to have a different key. So you would say first name for the first name, last name for the last name, okay? Something like that. So for example, if you wanted to print the person's name, you would simply use this structure. You would say print person1 and square brackets and inverted commas, the actual key, and it would print the name Ahmed and date of birth and so on. Okay, so this is similar to something called record. You might be studying this in other courses. For example, in Introduction to Computing, Introduction to Programming, you might this thing might be referred to as a record. But in Python, this closest thing to a record is something called a dictionary. Okay. So if you think about this, and you think about how one could form a data structure, a linked list, then what we just studied is essentially similar to what? If you think about this data structure, that person, how would you place that person in here? Okay, so these are the nodes, and these nodes are linked. So what resemblance do you see between Python and a linked list? Okay, how do you relate this person here to a linked list like this? Can somebody try to explain that?
So Heather,
Jihad.
the key may be linked to the value using a pointer.
Okay. This could be the key, right? Or this could be, for example, if it's a string over here, this is a pointer. I got this wrong. It should be a pointer to buy. Okay. So I need to mute participants. Okay. So so what you're saying is that the key could be the value over here, for example, the pointer. Okay, keep going. And what would be the value? I've muted everybody, so you'll have to unmute yourself again. Okay, so let me
So the
help.
value could be stored in another virtual memory or something.
Okay, so if you think about this structure over here, and you think about the structure of a person, this doesn't at present have a pointer. If you think about it, this doesn't really have a pointer. All it has is the actual contents. Okay, and the actual contents over here were what? So this was essentially the contents, right? Well, let's just not worry about the pointer, but if you think about it, the actual contents were this, whether it's true or not, and the floating point number over here. But right now, we don't really know what this linked list actually means, all right? We don't really know what 20 is implying, whether is that, the person's age or what does by mean. So there is no real meaning over here, okay? So what Python is trying to do is trying to make it more useful. And this dictionary data structure is basically what it's doing is it's creating a node, okay? So this entire person one over here is essentially equivalent to a single node. And now what you may need to do is you may need to actually, for example, if you're trying to create an employees list, okay, or just a list of people in your phone book. So, and you want to store them in an ordered manner, right? So here you may have a list of employees and you're trying to save them in an ordered list or a phone book. Then the question is, how would you store it as a linked list? Okay, so this here so far person is just the contents of that node. How would you create a linked list out of this? Any thoughts? Okay, so this essentially this person one would it be correspond to one node over here, or it correspond to a large number of nodes? What do you think?
Sir, Mr.
Sir, Samir Hussain.
Ji Samir.
Sir, I guess initially we would have L1 and we would have 3 pointers pointing firstly name, then date of birth, and then the other things that are in the list.
Okay. Any other thoughts on this?
Sir, Shayan.
Jishan.
Sir, we could have one node for each key, and then like we could have separate lists in a list for different records.
So
In one list, we could have separate lists each for an individual record.
Okay, very good. So basically you could have a list which it comprises of different persons. So if you have a phone book, then person 1 could be one node. I think that's what you're saying. And you could have person 2 as another node in this, and you would have a different name. So this could be Ahmed, this could be Fatma or somebody else. And these, and you want it sorted, right? So what you would want to do is have a linked list in which it's sorted by the, let's say, it could have different values, how you're storing it, but let's say you're trying to sort it by the first name, okay? So if you have A and F over there, and you now want to insert somebody who has a name Zaitoon, for example, Z, so you would go through this linked list, you would say, well, it should be after A, it should be after F, and then you would enter it over here as Z, okay? And if you wanted to enter somebody who has the name starting with B, then again, you would go through this link and you would change the pointer and you insert somebody with the name of B, and you would change this pointer, something like we did earlier, okay? So that's how you could create a linked list of these dictionary items, okay? So I hope that is somewhat clear. So, so now let's say that this is the linked list, and this is pointing to each one of these persons. Now, can somebody tell me what should be, how should this person be represented in memory? So we can see that there's a name and there's different values. So if you have a linked list and you have different nodes, so here's node person 1, here's person 2, and so on. There are different questions over here. How would this be organized, and how would the linked list, now we're separating out the linked list from the actual nodes, okay? So how do you think this should be organized? So let's look at the linked list itself. So this is simply pointers to different nodes. So how do you think, how would you like to organize this data structure? You've already seen linked lists, so maybe you have some idea as to what should be over here. Any thoughts? How would you create a linked list of these employees, and each one of them consists of a node in memory?
Sir Shayan here.
Jishan.
Sir, in the first, in the first row of the employees, we could have the type as list, and then it could point towards a separate list of each individual employee.
So here you have a type list, and then it points to
a separate list which is contained within this for each individual employee.
Okay. All right, so that's one way to do it. Any other thoughts? So let's assume that this node here is person 1. Okay, this here node is person 2, and it has data for this person here. The name is, let's say, Ahmed, and this name here is, let's say, somebody with the name starting with B. Okay, let's say B now. So how do you link all of these together in memory so that it forms a linked list? How could you do that? So recall that in a linked list, normally at the end, we have a pointer to the next element. Okay, so does that make sense? And let's say this employees list has only got 3 employees. All right. So it would look something like this. Okay. G.
Sir, maybe the end of one dictionary could have a pointer to the other node, to the second node in the list.
Yeah. So what you could do is, as you were doing earlier, is that you could have a pointer over here, which points to the next one. Okay. But here what we've done is actually separated the pointers out. So we don't have a pointer over here. We could have done that, but what we've done over here is a slightly different data structure, and both of them are just as good, okay? But over here, I've simply made the pointers as part of a separate structure, okay? And so my question here is, what should be the contents of these?
Sir, it should contain the type dictionary
Okay,
or
right. But this is in a different location memory. So how do you know where this is being stored?
Sir,
Jiran?
so like for the first row, you point to the this node.
Okay, so what you're suggesting is that this first element could be a pointer to this,
Yeah,
okay?
yeah,
And
and
now we don't really know whether this is of type dictionary or not. That's what is perhaps confusing some people, okay? So what you're saying is that maybe the first element should be that this is of type dictionary, and the second should be of a pointer, just like we had earlier. We had a string, and then if it's an integer, we actually have the contents. But you see, the only difference over here is that this is a linked list of employees only, and each employee has a fixed structure. In other words, now we don't have the situation as we had earlier, that each one of us are a completely different data type, okay? So this was a bit random. If you think about this L1, the 10 and high and 5.3, that didn't really make sense. Here we're trying to do is slightly organize this, and we're saying that every employee will have 4 fields, essentially a name, date of birth, and the gender and the height, okay? So essentially, we don't really need to have this field which says that it's of type dictionary, okay? We could simply have a pointer over here, and then it would somehow be understood that each one of them is going to have the same structure, okay? However, there is some confusion over here as to what should be the contents of this. So now, hopefully, you can see that the first element is now going to be a pointer to every node. So there's not going to be a pointer over here. This slightly different architecture. And each one of them is just going to be the contents of the node. And the pointers have been put in over here. Now, can somebody suggest what should be the structure of the actual node in memory? So we're trying to store all of this in memory. Any thoughts? And it's going to be fixed. So every person is going to start with a name, then is going to have a name, and then the next field is going to be, the next key is going to be date of birth, and the next one is going to be the gender, and so on. Okay, that's going to
sir,
be
it could be
Brian,
yeah.
it could be a linked list.
So it could be a linked
Another
list
linked
itself. Okay, but do you think that we need a linked list over here? Do we need to have a linked list of each one of these? When is a linked list useful, and when is an array more useful?
Sir, a linked list would be required when the contents would be non-contiguous, but here we need contiguous memory.
Okay.
So we could have an array, but the thing is that all the values are of different data types. So
Yeah.
that's why it's a bit confusing.
Yeah. So it is a bit confusing. So you could come up with different data structures. I mean, there's no single solution to this. But let's take a look at one possible solution. All right, so you've already seen this, that we've got the node pointer over here, which is pointing to a node, and the next pointer over here is pointing to the next linked list node. And now we're looking at the structure of a particular node. And so here's one solution. So, and this is, there could be other solutions as well. So let's say that the first portion, the first element in this node is the name. Okay, is actually the string NAME. Okay, and that corresponds to the first key. And then, since the first key is of type string, so this is of type string, we then need to have a pointer over here. Okay, so here we're pointing it to another portion in memory, which is going to have a variable length, because as you can see, you could have a very long name over here or a very short name. So you could fix it over here, but if you fix it over here, you would have to keep space for the longest name, and then you would have to arbitrarily decide whether the amount of space for the longest name is going to be 100 characters or 200 characters. And then if the name is really short, then you would end up being wasteful. Okay, the same issue of arrays versus linked lists. The next one is date of birth. So you could have the string over here, date of birth. Not sure why people unmute themselves. The next element could be the date of birth. So this would be a string which has the actual key in it. And since the date of birth is an integer, we don't need to have this as a separate pointer. Subsequent to that, we could have a string which is specifying the next key value. And then after that, since this is Boolean, we could have, for example, 1 byte, which would specify either true or false. And then we could actually store the next key value. So notice that we're having key and value, alternate, key, value, and this is a key, and this is value. Why is that? Because we're trying to save all of this data. Okay, so some of these values are actually fixed. So name, DOB, male, and height, these would always be repeating. And maybe it's not the best data structure, but this is one solution. And then you have a Genital.
I wanted to ask, why are we using two different lists? Why not use a pointer after 5.5?
Okay, so as I said, you could do that. You could do that. So I'm just showing you alternate structures. All right. So as I said, there is no single structure which is perfect. In order to compare different data structures, you'd have to see in terms of all the analysis that we normally do, is one better than the other in terms of searching, is one better than the other in terms of insertion or deletion, or in terms of memory usage. Okay, so there is no single solution to all of these questions. Okay, but this I'm just showing you one possible solution. Another possible solution would be that instead of having all of this, we simply have employees point over here, and we have the next pointer point simply like that. Okay, so perfectly fine. All right, but this is a little bit more organized. As you can see that the linked list itself is separated from the actual nodes, and that's how a lot of times these structures are defined. Okay, so hopefully
Sir Musab,
Ji Musab.
I have a question. Over here we have just 3 nodes. But in the case of if we have, for example, thousands of nodes, it will be quite tedious to go from node to find a certain person.
Yeah.
So could we use binary search over here?
Yeah, we
somehow?
could. So remember in the previous lecture, we said that if we want to expedite this, we need to have a better solution. Okay, so this is where we started off, and we said that this is too tedious, and that's where we sort of going. And I hope that we can get to that at the end of this lecture. Okay, so if you remember, even though this is sorted, in the previous lecture we said that because you have to go through this entire linked list, even though this is sorted, you can't do binary search. And I hope you remember why we can't do binary search in a linked list. Okay, simply because it's not an array. You can't arbitrarily go to the middle of the linked list. You have to go from pointer to pointer. But hopefully by the end of this lecture, we'll have a solution for that. Okay, but to get to that, I need to show you some different versions of linked lists so that you can understand it better. But we're slowly getting there. Okay, so let's see, how are we doing on time? Okay, so this was one solution to the linked list. Now let's take a look at another example, which will now show you the power of these linked lists further. Now suppose that we were implementing the Fibonacci sequence, and this was, I think, right at the beginning of the course. I think the first homework assignment had this as an optional assignment, okay? And many of you were able to solve it. So a Fibonacci sequence is simply the numbers that go with 0, 1, starting with, if n is equal to 0, Fibonacci of 0 is 0, Fibonacci of 1 is 1, and Fibonacci of 2 is simply the sum of these two, so it's again 1. Fibonacci of 3 is the sum of these two, so it's 2. Fibonacci of 4 is the sum of these two, so it is 3. Okay, so that's how the Fibonacci sequence works, is that it simply takes the sum of the previous two and adds it, sum of the previous two and keeps on adding it. Okay, so now the question is that if we implemented this using recursive solutions. So some of you actually got this in the first lecture. And this is a solution. So let's try to see how this works. We're defining a Fibonacci sequence, which takes a number n as a variable, and just printing out the variable n so we can see the output over here. If n is equal to 0, we're going to return a 0. Why? Because Fibonacci of 0 is 0. If n is equal to 1, this is the start, this is the initialization of the Fibonacci sequence. If n is equal to 1, you're going to return a 1. If anything else, any number which is presumably larger than 1, then you're going to take this, the sum of the previous two Fibonacci values. So if you're doing Fibonacci of 2, you'll take Fibonacci of 1 and Fibonacci of 0. Okay. Now, in order to calculate this, you would have to again go through the recursive function. Okay. So let's try to see how this whole process would be stored in memory. Okay. And in order to understand that, let's do a bit of a review of some of the items we discussed some time back. So we looked at the queue versus a stack. Okay, a FIFO queue versus a stack. Remember, a stack is last in, first out. And we looked at a recursive algorithm for doing factorial, which was a little simpler than Fibonacci. Factorial is simply n times n minus 1 times n minus 2 all the way till 1. So what we did earlier was that we said that if you want to calculate the factorial of 4, you would say factor 4 times the factorial of 3. This is how we implemented it, if you remember. Return n times the factorial of a slightly smaller number. So it would say, well, I don't know this answer, so I'm going to store this process in memory. Okay, it's going to be pending. I'm going to try to calculate factorial of 3, but I don't know what factorial of 3 is, so I'm going to say it's going to be 3 times factorial of 2. So I'm going to keep all of this in memory. So this is a sort of a stack building up. It would build up all the way till the top, and then it would, so the last item, it's going to be a LIFO, last in, first out. So now once you have factorial of 0, you know that, you can put that in over here, and you know what factorial of 1 is. And so you go down in the sequence, and eventually you'll find out what factorial of 4 is because you have all the previous results. Now, this was the simple case where you were doing a factorial which was only dependent on the function, the recursive function, but just it was only dependent on one other factorial equation. Now, what's the difference between the factorial implementation, the recursive factorial implementation, and the Fibonacci factorial implementation? Can somebody try to explain the structural difference between these two? In terms of recursion, what's the structural difference between these two recursive equations, recursive functions? Of course, there are some things that terminate. This, in this case, it terminates when it's the number n is equal to 0 or 1. In the factorial, it was terminating only on when n is equal to 0. Okay, and then if you look at this, that should give you a clue as to what is the fundamental difference between the factorial recursive implementation. GRAM. GRAM.
Yeah, yes, it's been called 2 times.
Sorry?
So It's been called 2 times.
2 times, yeah. So it's actually dependent on 2 Fibonacci's. The factorial only depended on one, on a smaller version of its own factorial only. But here now it depends on a sum of 2 factorials. Okay. So now let's try to figure out how would the stack actually work. So if you think about it, can you implement it as a simple stack? Because if you said Fibonacci of 4, it would say Fibonacci of 4 plus Fibonacci of 3. Okay, so it would actually, it's forking out. It's now creating, it now needs the solution of two smaller problems. Okay. So what do you think is the data structure looks like now of the stack? Can somebody give an idea of the data structure? It'll be a tree, you said, right?
Yes.
Very good. G. So it would definitely be a tree. So if people are familiar with what a tree looks like, so you know that a tree goes like this and has branches, and then you have branches and you have more branches, right? So that's what a tree looks like. So this is sort of like an inverted tree. Okay, it starts off from the top. You're trying to calculate the Fibonacci of 4. Okay, the Fibonacci of 4 is going to say, well, I really don't know what Fibonacci of 4 is. It's simply the sum of Fibonacci of 3 plus the sum of Fibonacci of 2. Okay, so it needs to have both of those solutions before it can actually calculate the result. And then it says, well, Fibonacci of 3, it actually depends on Fibonacci of 2 and Fibonacci of 1, right? It has to add these ones, right? And Fibonacci of 2 actually depends on Fibonacci of 1 and Fibonacci of 0. Fibonacci of 1 actually is fine. It's a terminating condition. 2 over here, Fibonacci of 2 depends on, again, 1 and Fibonacci of 0. And both of these are terminal conditions. All right. So these are sort of leaves of the tree. So you have leaves and then you have nodes which actually branch off. Okay. So now you can see that it's more the stack itself, which is managing the memory of the processes, is now itself a binary tree. Okay. It can't simply be a simple stack. The stack itself now is growing like a tree. Now, if something is growing like a tree, you can't simply keep it as a simple structure like an array. Over here, this could have been thought of as being kept in an array. Okay, but now because it's becoming wider and wider, it's dividing up and it's multiplying, so you can't keep it as an array. Okay, so clearly, I hope everybody is convinced that this can't be done. You can't keep this in memory. The stack cannot be implemented as an array. It can perhaps be implemented as a linked list. Okay, why is that? Because now we can have a linked list which is pointing to each one of these. Okay, so can somebody tell me what would be the structure of the linked list? Okay, so we've already seen this. Now, what would be the implementation in a linked list, and how would you organize the linked list? So we've seen a doubly linked list earlier. We've seen single linked lists. We've seen various types of linked lists so far. Okay. Now, can you put on your thinking caps? And I think I showed you the next slide by mistake, but let's try to think what would be the structure of the linked list. Okay, what would be at the root? So clearly you're going to have a bunch of nodes connected to each other. What do you think should be the node and what should be the content of each node? Let's say this is a node. Okay, and let's say one of the elements in the node is the actual process that you're trying to figure out. So let's say you're trying to do f of 4, Fibonacci of 4. Okay, so what should be other elements inside that linked list? It's probably going to be pointers and some other things.
Sir, each node will have 2 pointers that will go towards different sides of the tree.
Okay, very good. So Mustafa is suggesting that you could, because we know that this is sort of a binary tree and it's going to go into both a left and a right direction. It's a binary tree. Binary, by the way, obviously implies that each node will only have two subnodes. Okay, and that's why the word binary is being used. So, so clearly, if there are two subnodes, then you need to have two pointers if it's a linked list. Okay, so you need to have a pointer over here, and you need to have a pointer over here. Okay, so you can call this the left pointer, and you can call this the right pointer. Okay, so in order to calculate Fibonacci of 4, you're going to start a new process, which is going to say Fibonacci of 3 and Fibonacci of 2. Okay, and then this is again going to have another pointer, and so on. Okay, so you can see that this is how we're going to progress: a left pointer and a right pointer, and so on. Okay, so I hope this is all clear. Eventually, you're going to get to the leaves. So when you get to f of 1, it's not going to start a new process. It's simply going to say, well, I know what f of 1 is. Why? Because f of 1 is given to be when n is equal to 1. It's simply going to return 1. It's not going to start two new recursive function calls. Okay. So I hope people are clear with this. And I've got a question over here. Any thoughts? Do you think we need a parent pointer? Are we missing any other pointers? Do we need to have other pointers? I mean, do we need to have a pointer from here to here, here to here? I've just got a left and right pointer, so I'm just giving you thoughts. I mean, is this data structure complete? This is what a data structure implies, that, how are you storing this in memory? So any thoughts? Would you need to have a parent pointer or any other pointers? Remember, we had a doubly linked list, and in that we had a pointer to the previous node. But here it's sort of a tree. So a tree, an inverted tree, and it's going in the downward direction. So you can think of as this the head. All right. This is called a rooted tree, by the way. Right? Why? Because one of these elements is at the root of the tree. And then it has nodes, okay? And these are referred to as leaves. This is a leaf, okay? And these are branching nodes. Branching nodes, okay? And this is the head. So do we need to have a parent pointer?
Sir. Sir Shahan here.
Yes,
Sir, since leaves are automatically, it's eminent that they are branching out of a node, so we do not need to have to go back, because we are already declaring that a leaf is like it's a child of a certain parent node.
Okay.
So we don't need to. It would be kind of redundant if we declared that this is the parent of that.
So let's just forget about the leaf for a minute. Okay, let's look at this branching node. We compute this as 1, and we compute this as 0, and we calculate Fibonacci of 2 as 1 plus 0, which is equal to 1. Right? Now we need to pass this on. What are we going to do with this number 1? Fibonacci of 2. What are we going to do with it?
Since now it is the value of Fibonacci 2, then it's just going to be added with Fibonacci of 1, and then Fibonacci of 3 will be updated, and then so the same will happen with the.
Yeah, so if you think about it, if you think about this structure over here, this could have been stored in array, okay? And when you pop this out, you could simply figure out that the previous factorial of 1, once you've done factorial of 0, you know that factorial of 1 is probably just below it in memory, and each one of them could be maybe taking a fixed amount of contiguous space, okay? So once you've done this, you could actually go ahead and implement this, okay? But what happens when these are implemented as stacks? Okay, so now they're not in contiguous memory locations. So if you've computed f of 2, Fibonacci of 2, you don't really know where Fibonacci of 3, that process is in memory. Okay, so these are processes which are pending. And the only way you can go from one process to another that Fibonacci of 2 can pass on its result to Fibonacci of 3 is if it knows where this process is located in memory. So do you see the problem? And now, can you suggest whether we need to have a solution or not besides this?
Yes, sir.
Yeah, so Ryan, so are you saying like if you have a parent pointer to which there should also be a back pointer for every
Yeah.
node?
So
which is the
basically,
pointer?
what you're saying is that a back pointer would be needed, and a back pointer can be thought of as a parent pointer. Why are we calling it a parent pointer? Why? Because you can think of this as the child. Okay. So this is basically two children of this parent, and this is again children of the parent. And so we need to have a pointer which is going back to the parent. Okay. So here is the solution to that. We could have another pointer over here. You can see how the data structure is now being organized. You have a left pointer and a right pointer. Okay. And now you also have a parent pointer. And in the case of the head pointer, the head node, the parent pointer would be null. But for others, there would be a parent pointer which would point to the location in memory where the parent pointer is located. Okay. So I hope things are clear so far.
So Ryan,
Yeah.
what if there were what if the function was being called 3 times? Would there be a middle pointer too?
So say that again. You're saying the function f3 dies, did you say?
No, not dice. I mean, if it was being called three
Yeah.
times,
3 times.
if a
Okay.
function, any function was being called 3 times.
Good point. So your question is that what if this function is being called several times? And exactly what is your question after that?
Yeah, would it have a middle pointer, or like it would the pointers increase proportionally to the times you call?
Okay, so you raised an
the
important point. You see, when you're doing this, how many times is let's say f2 being called? When you're calculating f4, how many times is f2 being called? Clearly, once over here and once over here. Okay. Now you can imagine that as this process becomes larger and larger, if you're doing f of 5, it's going to do f of 3 over here as well. Okay. And so f of 3 is going to be called once over here and once over here. Now, in this recursive implementation, do you think the result of f of 3 over here and f of 3 here, or the result of f2 here and f2 over here are going to be used? Or is it going to calculate it all over again? Look at this implementation. Would it calculate f of 2 all over twice, or would it do it and it would be intelligent and say, well, I already calculated f2. I don't need to calculate it again. I should maybe use that previous result. Can somebody tell me the answer to this question? Would f of 2 be called twice, or would it be called once?
So it'll be called once.
Be called once. Okay. Can somebody look at this trace over here, and that might give you an idea?
Sir, the trace shows that it's called twice.
being-
And
so-
in fact, every number except the root or 3 is
And
called
3, yeah.
twice.
So you can see that if you're doing f of 100, right, this would be an extremely inefficient way to actually do this problem. Why? Because it's going to calculate f of 99 and f of 98. And then 99 is going to calculate f of 98 and so on. And then it's going to do f of 98 all over again. Okay. So this is not a good implementation. And if you try to actually calculate the complexity of this in terms of time and so on, it would not be very good. Okay. But this is just a very simple solution. Why is it simple? Because you can see that the algorithm is very simple, but the complexity is not good. Okay. So coming back to this, we've got a solution where you have a parent pointer, and the parent pointer would allow the stack to actually operate properly. So you've got, once you solve this, you know where how to get to the parent process. Okay, so you can see that this is one example of a binary tree where you have 3 pointers, and only the actual data is fairly limited, but the overhead is fairly high. Okay. Is there a question?
Yes, sir, Nidal.
Ji, Nidal.
Sir, even when we're using 3 pointers, it will be called multiple times, right? So it is still inefficient.
It is still what?
Inefficient.
Yes, it is very inefficient. So it's a very inefficient implementation, but the algorithm is very simple. You can see that the algorithm is, it's just returning Fibonacci of n-1 and Fibonacci of n-2. Okay, there could be an iterative solution to this, and some people actually implemented that in homework 1, and that may not be so elegant solution. It's such an elegant solution, but it might actually be far better in terms of the complexity, both time and space. Okay. So now I'm not going to look at the time and space complexity over here, but I'll just keep going, because we're trying to get to a particular solution for the search problem, which we started off with. And I'm trying to find a solution to that in the next 5 minutes. Okay. So this is an implementation of a binary tree. And now what I want to introduce to you is something called a binary search tree. Okay. And this is where things are now coming to an interesting conclusion. A binary search tree, I'm going to define it as follows. The way you create a binary search tree is an interesting way. What you say is that I'm going to, if I need to create an ordered list, I'm going to create it in the following manner. So suppose I'm getting these bunch of numbers. These are telephone numbers, for example. The first number that you get is 52. So we put 52 at the head of the binary tree. Okay, so this is a binary tree. And then the next number, this is going to be a linked list. And the next number is going to be on the left side if it is smaller, and on the right side if it is bigger than this number. Okay, so where will number 23 be? Clearly it will be over here. And the number 77 will be over here because it's bigger than 52. Okay. Now, where will the number 65 go? Can somebody tell me? 65 is going to be compared with this. Is it bigger or smaller? Clearly it's bigger. It's going to go on the right side. Now it's going to again compare it with this number. So is 65 bigger or smaller than 77? Smaller. Okay. It's going to go on the left side of this, on the left pointer. Similarly, the number 9, and I'm trying to hurry this up. So you can see the number 9 is going to go in this direction. Then it's going to compare it with number 23, and you're going to put it in the left pointer. Okay. So if you do all of these, you're going to end up with the following tree. 23, and then and you can follow this through, but this is the tree structure that you're going to get. Now let's try to do a search. Let's suppose that we're searching for the number, for example, this number over here, 47. Okay. How long do you think it's going to take? Can somebody give me an order of magnitude? So if there are n numbers over here, n numbers here, you think it's going to take order of n? It's going to take order of n squared? Is it going to take order of log n? Is it going to be order of 1? How long do you think it's going to take the n numbers here to search for any number? What's your gut feeling?
Sir, order of log n, because it's definitely not n. It won't have to traverse all the numbers.
Yeah.
You will have to traverse a certain branch.
Yes, exactly. So you've got the gut feeling is right. It's going to be order of log n. Why? Because 47, you're going to say, well, 47 is on the left side. So you see what we've basically done is we've done a binary search. Okay, and that's why it's called a binary search tree. So binary tree as well as a binary search. Both of these are combined into one. And so it's going to go on the left side, and then it's going to say, is 47 bigger or smaller than 23? It's bigger, so it's going to go this side, and eventually it's going to come here. So the complexity is essentially going to be of the order of h, where h is the height of the tree. And perhaps you can convince yourself that the height of this is going to be of the order of log n. And I'm not going to prove that, but maybe your gut feeling is going to tell you that this is going to be of the order of, that the relationship between h and n is going to be order of log n. In other words, h is going to be of the order of log n. Okay. And I'm not going to prove that right now. But what if, and so the solution is very interesting. So the search is also going to take order of log n. Insertion is also going to take order of log n. Why? Because you're going to do the same thing. You're going to add a number over here. You're going to go all the way down over here, and you're going to add a number. The deletion is also, and deletion is a little bit more complex, because if you delete this, it becomes, the tree changes. But without proving this, you'll have to believe me that all of these actually take order of log n. Okay. So essentially, we've now come to a solution which says that we've got a data structure which is what we were searching for. And now we've got a data structure type D, which is a binary search tree. And now the search takes order of log n. All right. Insert takes order of log n, deletion takes order of log n, and is it wasteful or is it efficient in terms of memory utilization? Clearly, it's efficient. Why? Because it's a linked list and it's not using contiguous memory. Okay. So finally, we've got a solution which is now better. It's actually superior than all the other solutions, because all of these values are order of log n, and even the memory utilization is efficient. Okay. So this sort of almost concludes the section on data structures.
Ryan, can you go back to the like previous two slides?
Yeah.
Previous two slides. Yeah. One more.
Yeah.
One more. Yeah. One more. Yeah. Right there. So, is there any way for us to, for example, once you give F2 for that to point to the other F2, that it isn't, computed
Okay.
for the other one.
Okay, so you're trying to think very creatively, and that's excellent. What you're saying is that somehow, if this can have a pointer to this, and you can save this computation again, and you can actually keep track of previous. So what you could do is you could have a memory, another structured memory, and every time you compute Fibonacci of a number, let's say Fibonacci of n, you actually store it in memory as well, and you store the number over here. So then what it's going to do is going to say, well, Fibonacci of 2, it does a lookup in this other memory and says, and this could actually be stored as an array perhaps, or maybe another linked list as well. But this is now making it more complex. And this is maybe something that you'll think about in an advanced course where you're trying to improve the data structure to actually even improve this. Okay, but that's the right thing, that right way to think about it, that you need to find better solutions and excellent thinking. Okay, but I'm not going to try to solve that over here. But let's just take one more quick look at the binary search tree and see what happens when, well, we're almost out of time, but I'll take another couple of minutes. What happens when the numbers are not given to you in a particular order? Now, the numbers I had chosen over here were very carefully chosen, okay? And you got something which is called a balanced search tree, okay, binary tree. Now, what happens if you get these numbers? So let's say you get the number 23 over here, okay? And then you get the number 15 and so on. What you see is that you'll have a very unbalanced search tree, okay? It's imbalanced. So the left side over here is small, the right side over here is small, some of these trees. So it's like a typical real tree, okay? So it's not really properly balanced. Now, in this case, do you think it's still going to be order of log n? Clearly not. Why? because as I said, it's going to be perhaps order of the height. So the complexity is actually going to be order of h and not order of log n. And in this case, you can imagine that in the worst case, the binary tree could be actually a single tree, something like this, which is simply not binary at all. Everything is left-sided. In other words, if you somehow you got all the numbers in such a way that it was completely lopsided, in which case it would actually be order of n. But there are techniques to actually balance these unbalanced trees as well. So hopefully this gives you an idea of how to change, to have a data structure in such a way that you can optimize various operations, including the memory utilization. Okay, so this is where we'll
Understood.
stop at in terms of data structures. Jivan.
The lopsided tree will be a sorted tree, right?
Yes, so this is all sorted. Okay, yeah. Because the ultimate idea is that we want to have this binary search tree be sorted so that we can actually improve the search. But if somehow the numbers that are being presented are not in a specific order, then there are chances that in most cases it will be slightly imbalanced. But if in the worst case, it's possible that it could be completely lopsided, in which case it would not be order of log n, it would actually be order of h, which would make it order of n. So the worst case is order of n, but on average, it will be order of log n.